I'm going to go through some problems on fatigue with you. There are a couple of notes before we start solving those problems. First, we are going to ignore the effect of size, reliability, surface finish, temperature, etc. When we solve these problems. This is actually not for real, and in your project you need to consider those effects. Second, because we are going to extract some of the information from charts, so you might get like slightly different results compared to what we have here. So the first problem, problem number 1 here, it says we have a long steel bar of rectangular section with width d and thickness t. So if you look here at this picture, you see here the width is d or w, and the thickness of this bar is t, denoted as t. It has bolt holes of diameter d on the center line, each at a distance d/2 from the end, from each end. So you see here, this is the hole, this is the bolt hole, one on this side and one on the opposite side. The diameter of the pen that goes through this hole is small d, and the distance between the edge to the center of the hole is denoted as h, which is d/2, which is the width of the bar divided by 2. So this h here is equal to d/2. A tensile load, as you see here, we have a tensile load on the bar acting along the axis, is transmitted by bends in the holes with axes which are normal to the surface of the width d. So just in short, you see here this hole, the center line of the hole is perpendicular to the surface of the bar, and the load is applied here through this pen and the pen on the opposite side. So it just applies tensile stress to the bar. So specify the thickness t. So the thickness t here is unknown of the bar, in which case the width is 50 millimeters. So W here, or D, capital D, is 50 millimeter. The diameter of the pen here is 20 mil. Subjected to an axial tensile load which fluctuates from 4 kilonewton to 14 kilonewton. This is the minimum force, and this is the maximum force. So F minimum and F maximum are given here. The factor of safety is given as well as 1.5, and the material from which this bar is made is given. It is the yield strength of this material is 280 megapascal, and the endurance limit in tensile tension is given for a polished specimen 200. So this is the endurance limit of the material. And it says here, assume a notch sensitivity of unity. So small q here is equal to 1. This just means that k sub t is equal to k sub f. So the fatigue stress concentration factor k sub f is equal to the stress concentration factor k sub t. So the thickness is going to be about 6 mil here in this case. So these are the data that are given to us. The width of the bar is 50 mil. The diameter of the pen is 20. Notch sensitivity value Q is equal to 1. The load fluctuates between 4 to 14 kilonewton. The factor of safety is given as 1.5. The material characteristics are given. The yield strength is 280. The endurance strength is 200 megapascal. So in order to find the blade thickness here, we're going to use this equation, the Soderberg equation or criteria, where the factor of safety is equal to the yield strength of the material divided by the mean stress. Remember, this is the mean stress, not the mean force, because maximum and minimum forces are given, but we need to somehow to deal with that, plus the fatigue stress concentration factor is here times the yield strength of the material divided by the endurance strength of the material multiplied by the reversed stress. So we have the reversed stress here, and then we have the mean stress. So if we multiply the top and the bottom of this equation by A, the cross-sectional area, the minimum cross-sectional area, so the numerator here is going to be the yield strength multiplied by A, and when we multiply this denominator here by A, so the cross-sectional area multiplied by the mean stress gives us the mean force. And when you multiply the cross-sectional area or the minimum cross-sectional area by the radial or the reverse stress here, so it's going to give us the radial force again. So when you multiply the cross-sectional area by the reversed stress, it gives us the reversed force. So because we have the maximum and the minimum forces, so simply we can use these two equations to calculate the mean force and the reversed force. So the mean force is we add the maximum to the minimum and divide by 2. So it's 14 plus 4 over 2, which is 9 kilonewton. This is the mean force. And the reversed force is the maximum minus the minimum over 2, which is 5 kilonewton. So we have the mean force now and the reversed force. And then we have the yield strength, we have the endurance strength. So we need to find out the fatigue stress concentration factor, K sub F, and we need to find out the cross-sectional area or the minimum cross-sectional area as well. Remember, the cross-sectional area includes the thickness of the bar that is required. So first, when we assume that the notch sensitivity Q is equal to 1, this just means that the fatigue stress concentration factor, K sub F, is equal to the stress concentration factor that we find based on these charts, a set of charts. This is one of them. So these two values are equal now. So how we are going to find out the value, the fatigue stress concentration factor or the stress concentration factor from this chart? It's quite simple. So you look at the figure that was given to us, and then if we divide the diameter of the hole over the width, so this is the ratio between the diameter of the hole over the width of the bar. So the diameter of the hole was given as 20, the width of the bar is given as 50, so this gives us 0.4. Then we divide this distance here, the distance between the center line or the center point of the hole to the edge of the bar, divided by the width of the bar, so this gives us 0.5. Using these two pieces of information, we can use or extract the value of the stress concentration factor from this chart. First, the ratio D over W is 0.4. So we here, just at this 0.4, we draw a line, vertical line, until we intersect with the one of these three curves. The one curve that we need to intersect with is the H over W is equal to 0.5. So H over W is 0.5 here, then go to the left to find the value of K sub T, which is the stress concentration factor. In this case, they are equal, so we don't need to worry about this. So Kf is equal to almost 3.22. So these steps here are the same on the previous page. So now we're going to focus on the cross-sectional area. So in this case, we have just found the stress concentration around this hole here. So we're going to consider the minimum cross-sectional area across the hole. So it's W minus D, which is this dimension here, multiplied by the thickness of this bar, which is D. So this is the cross-sectional area or the minimum cross-sectional area. It's W minus D times D. So the width is 50, the diameter of the hole is 20, and the thickness is unknown. So this gives us 30 times the thickness D in millimeters squared. If we go back to the Soderberg equation and then we rearrange the equation, so we'll go back here and then we know that this is the factor of safety and this is the area. So the area here is equal this bracket multiplied by the factor of safety divided by its yield. This is exactly what we have here. The factor of safety multiplied by the bracket divided by its yield gives us A, or the cross-sectional area, or the minimum cross-sectional area. In this case, this left-hand side is known to us now, and then is equal to the area. Whatever we have from here, we equate it to 30T in order to find the thickness of the bar. So the factor of safety is given as 1.5. The mean force was calculated as 9 kilonewton or 9,000 Newton. The fatigue stress concentration factor was found based on the chart, it's 3.22. The yield strength and the endurance strength of the material are given, 280 and 200 in megapascal, and the reversed force is given as was calculated actually as 5 kilonewton or 5,000 Newton. This is divided by the yield strength of the material, and then whatever we have from here, we equate it to 30 T, which is the area, and this gives us 5.6 millimeter.